Hello and welcome to the first part of section 8.7. I'm going to go over Taylor and Maclaurin series. In the first part, I'll go over the definitions. Second part, I'll go over how to show that the Taylor series for a function is the same as the function. And then on my third part, I'll do a lot more examples going over limits, integrals, multiplication, divisions, and other things involving series, okay? So let me start by going over this theorem. This theorem tells me that if f has a power series representation, which is the same as an expansion, at a, that is, if I can write f of x as this infinite sum from 0 to infinity of cn times x minus n to the n, for the absolute value of x minus a less than r, then the coefficients are given by this formula, okay? What this formula does is it takes the nth derivative, okay? So the nth term in my expansion will involve the nth derivative of my function f, okay? So that tells me that I need a function that has enough derivatives, okay? Now, I'm going to go over this proof. It's informal, but just to give you an idea of where the coefficients come from, okay? So for example, imagine that you start with your f of x, which you're assuming you can write as a power series. So if I write the actual terms, I get c0 when n is equal to 0. When n is equal to 1, I get c0 plus c1 x minus a, and so on. Now, if I substitute a, this series is centered at a. If I substitute a, then I would get f of a, it's equal to, this goes away, this goes away, this goes away. Everything with a in it goes away. And I'm left with f of a being equal to c0. So that gives me the coefficient of the first term. Now, if I take the derivative, and I do exactly the same thing, if I take the derivative of my function f of x and I substitute a again, then I get that f prime of x is equal to, the constant goes away, I get c1, bring that 2 to the front, I get 2c2 x minus a, and so on. And then again, if I substitute a, everything with an a goes away. So this goes away, everything goes away, and you're left with c1 being equal to f prime of a, okay? So keep in mind that c0 is just a constant, so you get f of a. Then c1 is f prime, which is just the first derivative, okay? Now, it's not enough to see the pattern, so let's do one more. If you take the second derivative, and you plug in a, then again, everything with a in it goes away. So you get that 2c2 is equal to f prime of a. If you take the third derivative, and you plug in a again, then you get that everything with a goes away. And now you're left with 3 times 2, c3 is equal to f triple prime. If you take the fourth derivative, now the 4 comes to the front, so you're left with f, the fourth derivative is equal to 4, 3, 2. So notice that every time you take another derivative, right, you're multiplying by that next exponent, right? If I take the fifth derivative, then I'm going to have 5 times 4 times 3 times 2. So at the end, I think we're ready to see the pattern. We notice that f, and like the nth derivative of f, it's equal to n factorial times cn, but we're looking for the nth coefficient, so we write it like this, okay? We write it like this. Perfect, okay. So I'm going now to use this to define my Taylor polynomial, okay? Now the Taylor polynomial of degree n for f about a has the form, and then what I just said, right? It's just the sum, the infinite sum of, well, the cn coefficients are given by the nth derivative evaluated at a over n factorial times x minus a to the n, and this is what we have, okay? Now, the infinite series, as usual, is obtained by taking the limit as n goes to infinity of your Taylor polynomial of degree n. And this is called a Taylor polynomial of degree n because that's what we're doing. You have, as usual, right, when we deal with power series, we're getting a polynomial, okay? I get, if I ignore the rest, I have a constant. If I add this term, then I get a line. If I add one more term, I get a quadratic polynomial. If I get one more, I get a cubic polynomial, and so on, okay? Now, there's a special case, which is when a is equal to 0, we call it a Maclaurin series. So let me just make sure that you understand what's happening, okay? So I always refer to it's actually a it's actually a Taylor expansion, a Taylor series, a Taylor polynomial. Now, if a is equal to 0, then we call it Maclaurin, okay? So then all Maclaurin series are Taylor series, but not all Taylor series are Maclaurin series. Oh, I like that. Okay, and then let me make sure that you understand something else. Not all functions are equal to the power series. Now, in this class, we're going to focus on the cases where that is true. We're going to focus on the cases where the Taylor series, the Taylor expansion is equal to the function, but this is not always the case, okay? So that's what we're going to do in part 2 of this section. We're going to go over how to prove that the function and the Taylor expansion are indeed the same thing, okay? All right, perfect. So let's start by finding the Maclaurin series of e to the x. So then again, Maclaurin series means that I have to find the Taylor series or the Taylor expansions of e to the x about a equals 0. So let's just make sure that we understand that the fact that we're calling this a Maclaurin series tells me that a is equal to 0, okay? Now, I know that. I'm going to use my information here. I'm going to call it MF, right? It's just the Maclaurin series of my function f. So I'm going to say let f of x be equal to e to the x. Then the Maclaurin expansion, it's equal to the sum from n equal to 0 to infinity of the nth derivative of my function e to the x, evaluated at 0, x minus 0 to the n, right? But then here it's just x to the n, so x to the n over n factorial, okay? Perfect. So then the beauty of this is, you know, that, well, the derivative, so if we have that f of x is equal to e to the x, f prime of x is equal to e to the x, f double prime of x is equal to e to the x, the nth derivative of e to the x is equal to e to the x. So all of them, when you plug in 0, you get 1, okay? So you can rewrite here your Maclaurin series as the sum from n equals 0 to infinity of x to the n over n factorial, okay? Perfect. So let me show you what I mean by this, right? This is equal to, this is equal to. So when n is equal to 0, you get, when n is equal to 0, you get 1. When n is equal to 1, you get plus, well, x over 1. When n is equal to 2, you get plus x squared over 2 factorial. When n is equal to 3, you get plus x cubed over 3 factorial, and so on, all the way to infinity, okay? Now, let me show you something real quick. Of course, I wrote a little code here in MATLAB, and it goes over the Taylor, well, the Maclaurin expansion of e to the x, right? Taking a different number of terms. So let's see, I'm going to run it here. I'm going to go Taylor x, and then it should be running somewhere in the background. There it is. So this is for n equals 3, n equals 4, n equals 5, n equals 6, meaning that's the number of terms I'm taking. So the more terms I take, the better the approximation looks. Now, what you have to understand is that I am writing the power series, right? The Maclaurin series, the Maclaurin series, or of the power series. I'm expanding this about 0, okay? So my approximation is super accurate when I am really close to 0, right? So check this out one more time. So when I'm really close to 0, it's perfect. A line, a parabola, then a cubic polynomial, and so on. Really good when we're about 0 here. But then maybe if you're far from 0, this is not a good approximation. Now, this one in particular, notice that it looks like the larger the degree of my polynomial, the larger the amount of terms that I take in my expansion, the better the approximation, okay? So yeah, I'm just gonna let you know that this is one of those cases where the Taylor expansion is exactly the same as the function, okay? That's super powerful. Okay, so this is what I was saying, okay? If you start with your 0, if n is equal to 0, you get a constant. If it's 1, you get a line. If it's 2, you get a quadratic polynomial. If it's 3, you get a cubic polynomial. And then the more terms you get, the closer to e to the x you get, okay? So it seems that e to the x is equal to the Maclaurin expansion or the Taylor expansion about 0. Now it turns out that this is always true. It turns out that indeed e to the x e to the x is equal to a Maclaurin expansion, and I'm going to show it. Okay, now the first step for me to show this is that the expansion that we found actually converges. So let me do that here. Okay, find the radius of convergence for the series that goes from 0 to infinity of x to the n over n factorial. We know how to do this, right? I'm going to use the ratio test. So ratio test. Using the ratio test, I know that, well, limit as n goes to infinity of an plus 1 over an. So this is my an. So an plus 1 over an, it's equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. And then I have to divide by the nth term, which is the same as multiplying by the reciprocal. So I get n factorial over x to the n. I'm going to simplify this thing. I get limit as n goes to infinity. Limit as n goes to infinity of, well, xn plus 1 over xn. I'm left with 1x. So x over, and then n plus 1 factorial is the same as n plus 1 times n factorial. Times n factorial. So that's that. I have the n factorial on top. So what am I left with? I am left with the limit as n goes to infinity of the absolute value of x, and then that goes away, 1 over n plus 1, which I'm going to write as, take the absolute value of x out, and you have the limit as n goes to infinity of 1 over n plus 1. Well, we know that this limit as n goes to infinity goes to 0. Therefore, this is equal to 0. This is equal to 0, less than 1, always, okay? This is always. This is regardless the value of x. Now, the fact that we get that this always converges, right, that we always get something less than 1 regardless the value of x, tells me that my radius of convergence is infinity, right? Like this converges for any value of x. So that's super important, okay? Regardless the value of x. That means that my radius of convergence, I'm going to say radius of convergence is infinity, okay? Super important. Now, in case you still don't remember what that means, that tells you that my interval of convergence, it's all real numbers, okay? All real numbers. Perfect. Now, don't forget that since this converges, since my series converges, then the limit as n goes to infinity of x to the n over n factorial, it's equal to 0 for any real number x. This is super important. I'm going to use it in my next video, okay? Awesome. That's all I have for the first one. Bye-bye.